All right, you guys, so here we go. So 11.1, number 12. This was the seed on a turntable problem. All right. So this was sort of our crash course into angular motion, right? So let's see, what do we know? So it tells us the seed on the turntable is rotating at a constant rate of 33 RPMs. So what does RPM stand for, you guys? Rotations per minute, right? So 33 rotations per minute. What would be a great thing to do to begin? Convert that to radians per second, right? Okay. I'm working on the same stuff with my honors students right now, and I kind of wrote down this sort of problem-solving sort of list of strategies. And the first thing is always convert your units to, standard metric meters, radians, and seconds. All right. So if you do this, it gives you it's like 3.47 radians per second. Is that right? Is that good? Okay, cool. I did that in my head. Remembered it. Okay, so let's see. It tells you that the seed is 6 centimeters from the rotation axis. So 6 centimeters is 0.06 meters. Why is that important, you guys? What's that a measure of? Good. That's the radius of rotation, right? And I guess I didn't label it. What is this 3.47 radians per second a measure of, you guys? Angular velocity, right? So remember, frequency and angular velocity really measure the same thing, right? The only difference is your units, okay? The frequency is rotations per minute or per second or whatever. Angular velocity is usually understood to be radians per second, okay? And in fact, I think, as a quick side note, this is an equation that's on your sheet, which I've always thought was kind of dumb, because all you're doing is the 2 pi is just converting rotations to radians, right? Okay, so, all right, let's see. So A wants to know what the acceleration is. Well, it's spinning at a constant rate. So why would there be any acceleration, you guys? Yeah, there's centripetal acceleration, right? Because of the change in direction, right? Okay, so what we learned, at the beginning of the year was centripetal acceleration is v squared over r, right? Okay, so I guess there's 2 ways of doing this, and I think it's probably instructive to hit both of them. Okay, so in order to do this, we got to figure out what v is, right? Okay, so to find our v, I think we got to use a jumper equation, right? So v is going to be omega r. So we know omega is 3.47 radians per second. Our radius is 0.06 meters. So when you multiply that, it gives you some number that I don't know off the top of my head. 3.47 times 0.06, so it gives you about 0.208 meters per second. Cool? Is everybody cool with the fact, I remember this was a struggle for some of you guys last year. When you use these jumper equations, when you multiply by the radius, you're basically just multiplying by a conversion factor. This is really 0.06 meters per radian. Okay, and so the radians cancel out and you end up with meters per second. Everybody cool? Okay, so there's my velocity, right? And so now I can do v squared over r to get the centripetal acceleration. Follow? All right, and it turns out, and I think on your, the AP equation sheet that you get when you take the test, it doesn't have this equation on it, which seems weird because it's a really sort of, it's an important equation. We learned that, pretty early on even last year, right? So why isn't it on there? Well, here's why. Do you guys agree that if you're moving in a circle, if you're like on a record or a merry-go-round or something, your velocity is going to depend on your radius, right? Okay? So we know that v is omega r, right? So a simple substitution gives you that, right? your r's cancel out and you get omega squared times r. So I think that on your equation sheet that you get the day of the AP test, this is the equation that they give you for centripetal acceleration. Why might that be a sort of more, I don't know, more fundamental equation for centripetal acceleration? If you're on a spinning merry-go-round, does your angular velocity depend on your radius? No, it's just, this is basically your frequency. It's how quickly you're going in a circle squared times your radius, right? So those are sort of slightly more intrinsic values, I guess. Okay? So the other way you could have solved this problem is to just, you were given your angular velocity and your radius, right? Angular velocity and radius. So you could have just done omega squared times r. Cool? All right. Questions with whatever that was? 12A. Okay. 12B says, what's the least coefficient of static friction to avoid slippage? So now we need to be thinking about our free body diagram. So if this is the record, and this is the seed sitting on it, what forces are going to act on this, you guys? So a lot of you said centripetal force. Great. Where does the centripetal force come from? Static friction, right? So if this is my circle, my centripetal force is going to be directed inwards, and it's caused by static friction. Okay? And there are two other forces, right? What are the other two forces, you guys? Gravity and normal force, right? So gravity is mg. What would the normal force be, you guys? Also mg, right? Okay. So, so we found our centripetal acceleration, right? In the previous part. I didn't even figure out what it was. What does it turn out to? What is that centripetal acceleration giving you guys from part A? 0.722 meters per second squared. Cool? So, we need to find a way to relate this acceleration to a coefficient of friction, right? Margaret, Maggie, please, yes. So, if I can get my smartboard to cooperate, I guess I would just say it's this. It's basically net force equals net force, right? My centripetal force is mass times acceleration. That's got to equal my net force. That's static friction. So that's my coefficient of static friction times my normal force. Follow? All right, and so your m's cancel out. We know g, so you can solve for your mu s, your coefficient. Cool, you guys? Yep. All right, and then part C says if the turntable underwent constant angular acceleration from rest in 0.25 seconds, then what is the least coefficient of friction to prevent slippage? Why the word slippage makes me uncomfortable. Okay, so now what's happening is this. So top view, here's my seed, and it's spinning around but speeding up as it goes. So now we're going to have two types of acceleration. There's going to be centripetal acceleration, which is 0.722 meters a second squared. Follow? There's also going to be tangential or linear acceleration to make it speed up, right? Does that make sense? All right. So we ought to be able to figure out what that is. Let's see. It says it underwent constant angular acceleration from rest in 0.25 seconds. So that tangential acceleration is, well, here, let's do this. So here's what we know. We know that the record began at rest. We know that the time is 0.25 seconds. I think we can find our final velocity, right? Have I done that yet anywhere? Oh, here. We know our angular velocity, so we can find our final velocity, right? Good? So, stupid smartboard. All right, so our VF should just be omega F times R, right? Just using a jumper. So our final angular velocity we said was it 0.347? No, 3.47. Radians per second times our radius of 0.06. Why do I feel like I already did this? I did already do this. I totally already did that. And it gives you a thing. 0.208, yeah, sorry. Meters per second. Okay. So now I can find my tangential acceleration, right? It's just VF minus VI over t. So do you guys understand what's going on there? There are two types of acceleration, right? The centripetal acceleration is measuring how quickly the direction is changing at that moment. Okay? And this tangential acceleration that I'm finding out right now is a measure of how quickly the speed is changing at that moment. Okay? So if you figure this out, you're going to get, what, 0.832 meters per second squared. Follow? All right. So,
is this 11.1 number 12?
yeah, this is still 11.1, number 12. We're on C, part C. All right. So, does everybody see what I did there? All right. So, do you guys agree that we could find our overall acceleration now? I mean, do you guys see these are two components, right? They're perpendicular to each other, right? Okay. Your centripetal acceleration is always along the radius. Your tangential acceleration is tangent to the circle, so perpendicular to the radius. So just do Pythagorean theorem. That'll give you your overall acceleration. And then it becomes net force equals net force again. Okay? I'll do it in a second. Adam?
So after you work with the components, you find like the net acceleration, that's basically called the angular acceleration, right?
Say that again?
Like after you like find
The hypotenuse.
yeah. Is that then net angular acceleration?
No, it's still linear acceleration because your units are still going to be meters per second squared. Right? So the idea is, at this instant, there has to be an acceleration upwards to make it speed up, and an acceleration inwards to cause it to change direction. So this is my overall sort of linear acceleration. Okay?
Yeah.
Does that make sense, you guys? Okay, and so then again, at that point, it's going to be net force equals net force. So we know our mass. You just found your new acceleration. Whatever this red one is, we'll just call it A. That's got to equal your coefficient of static friction times mg, right? Because your normal force hasn't changed. So the idea is now that force of friction is playing two roles. One, it's providing the centripetal force to cause it to turn. Two, it's providing a tangential force to cause it to speed up. Make sense, you guys, or no? I know, day after break, I'm not any more excited about it than you guys are, if it helps. Yeah. Yeah, that's, I didn't actually do the math. It's this hypotenuse here would be.
Oh, that's the same thing.
Yeah, I'm sorry. So here it's, I don't have enough room. So we found our centripetal acceleration. It was 0.722. Over here I've got my tangential acceleration drawn there, but really when you add vectors you have to draw them head to tail. So here's my tangential. And this is A that I'm talking about here.
Yes.
Good? Everybody good? Thank you. Yep, that would be meters per second squared. Yeah, you guys, anytime you do this, this is the second person now who's asked about this. The only way you can make a vector triangle, you guys, is if all three sides of that triangle have the same units. Okay? All right. Any other questions on 12? Good? Trying not to call attention.
These weren't originally the same units, right?
What weren't?
These two acceleration vectors?
Sure they are.
They are. They've been.
Yep.
Okay.
Because centripetal acceleration, by definition, it's a linear value. You're measuring how quickly the direction of your linear velocity is changing.
Okay.
Is that a genuine okay or a?
I'll probably have to do a couple more. I think, yeah. Yep.
All right. Are we good?
Yep.
All right. So that was number 12.